Okay, take two. And because we were all waiting for our friend to come, so we delayed the lecture and we're going to start it now. So, we were talking about fundamental types and what they are in C++. We said that fundamental types are essentially to tell to the compiler what to do, how to interpret the bits that are stored in memory, and what operations are allowed on that. And this is the most building block of C++, these fundamental types. They include integers, floating point numbers, booleans, characters, and some relative concepts. So, integers. We know what they are, you know exactly how to create them, and the postfix for the literal values essentially dictates what these fundamental types are. Crystal clear. I'm going to go through this very quickly, so if you have any questions, stop me, okay, like you did for the thing, so we'll go through it. Again, review and fill in the blanks at the same time. And if you want to deal with unsigned values, you can always add the tag unsigned at the beginning of every single integer variable. Then that doubles the value and doubles the size of the integer and removes the negative parts from it, and it becomes an unsigned integer that you have. You good? Floating point types. Floating point types are float, double, and long double. Float, double, and long double. And unlike integers that how big the number in an integer can be essentially exactly corresponds to the number of bits inside an integer. It's 2 to the power of that one. Whatever it is, that will be the size that integer can hold. With floating point numbers, it's a bit different. It holds two parts, essentially. It holds in scientific notation, which is essentially a whole part and the decimal part, and then it holds the number of the exponent that it's supposed to be multiplied into. And because of that fact, they are not precise at all. We're going to go through in detail exactly what does it mean, but for now, just be aware that float and double. Float can hold up to 7 digits in total, precise. More than that, it's not going to be precise. And when I say 7 digits, it's not 7 digits after the decimal point. It's 7 digits in total. So 1, 2, 3, 4, 5, 6, 7 is the same, has the same precision as 1, 2, 3, 4, 5, 6, 7. No decimal point in the middle. If you add 1, 8 after any of those, you might lose the data. That's what precision means, essentially. In double, it's 15. In long double, it depends on your platform. Okay? And I'll go through it soon. We good? Now, in mathematics, we call integers integrals, and we call floating points real numbers. Okay? Boolean is essentially the answer for the cry that non-C people hated, the fact that C language didn't have a type Boolean and said 0 is false and anything by false is 0. It's already considered the truth or falsehood. And for type safety, they actually added a type Boolean. So Boolean, what it does, no matter what you put inside a Boolean variable, if it's a non-zero value, it will set it to 1, which is true, True. And if you put 0 in it, it is false, False. The value in, so essentially Boolean is an integer that can hold 0 or 1 only. What is good about it is that it actually can actually return state your intention when you are actually dealing with your language. So in C language, we returned an integer and we said it returns true or false, which essentially means if it returned a non-zero value, it was true, and if it was 0, it was false. But when you're returning a Boolean, you're essentially telling that, hey, this thing is returning truth or falsehood, and the person's not supposed to, the person's not going to guess it. Character types, I am mentioning it separately, not because they are separate from B, C, D. Now, I mentioned character types not because they are separate from integer values. They are exactly an integer. It's essentially a small integer, but because their size is suitable to hold ASCII code of something, they are used as characters. So single quote, so the literal value that you write single quote A, single quote, it is essentially a character with specific ASCII code. So line number 5, it's actually 65. That goes to A. Okay, just be aware of that. And you can always, to actually see what the values are, because insertion operator is a polymorphic operator. If you do not cast it, it will show the value. It will show the shape of the ASCII code, because the insertion operator knows it's a character. It actually shows the graphics of the character. If you want to actually see the code, you have to cast it to an integer, and you know how. We good? You're okay? Remember static cast, right? From OOP345? Yeah. Oh, come on. Void type, we talked about it before. I'm going to talk about it again. Void type is essentially when you don't have anything to return, you call it void. In C language, when we are actually creating a function that is void, we put void inside the parentheses. In C++, we don't. That's just the difference between the syntax. So essentially, saying void, it means no value is being returned. Okay, it returns nothing. That's a void type. And we don't have a void type variable. You cannot say void A. It doesn't make sense. If you want nothing, don't create it. As easy as that. We talked about initialization, different types of initializations that we have, and I've already covered this in OOP345, but in 345 I'm just going to mention you. If you are not my 244 student, this is what it is. So line number 5 and line number 6, they are initialization from C language. Okay, it still works in C++, there's no problem with it, but we now go for a type-safe universal form. That is line number 7, and I expect everybody initialize their stuff like that. That assignment at line 8 is redundant. You don't need to put it, okay? So anything, literally what I meant, anything, any object that can be initialized, you can initialize it with curly brackets, okay? And if you put empty curly brackets, essentially that value will be defaulted. Now, if you have a structure and you set it to curly bracket, it sets all its members to 0 as structure. I didn't say a class. Okay? If there is a class, if you put empty curly brackets, it's its default constructor, whatever it is being default. Other than that, in front of anything, it literally sets all the bits to 0. So if you have an array, you put something empty in front of it like that, all the elements of the array and the bits inside will be set to 0. So don't loop through the array to set them to 0. It's just unprofessional. And if you put it, for example, in front of a pointer, it sets everything to 0. Therefore, it becomes null PTR. That's a universal way of initialization. So type inference is something that we are going to use a lot in 345 soon. Type inference essentially says, I'll tell you what the type is by looking at what you are initializing me into. Okay? So now I'm saying const auto n is equal to 6. Because 6 is an integer, that auto means integer. In line number 8, I'm going to say for I is equal to 0, it means it's a regular integer, because 0 is a regular integer. If I put over here u, then auto will be an unsigned integer. If I put over here l, then I will be a double, a float, sorry, a double. And if I do this, it's going to be a long double. Okay? So again, anything that you are dealing with, be careful. Auto takes the thing. Now, why we are using this now? There are several reasons for it. Sometimes the types are so ginormous that it takes a long time for you to go through it. If I have an unsigned long employee pointer, sorry, unsigned long double pointer, and that's a type, and I want to create another one and initialize it to something else, it's too long to write the whole thing, so I simply write auto, not to rewrite the whole thing over and over. So essentially, one good thing that it can do is this: it shortens the code. So if I have unsigned long pointer PTR, if I ever need to use that, I can set that, create another one that is set to that one. I can simply say auto A is equal to PTR, not to write the ginormous thing. I think just helpful, okay? But again, at the time that compiler is running this, this is supposed to be available. Otherwise, it will not be able to auto it. Now, this is for the covering the part that we are lazy and we don't want to type much. But soon we'll find out, when we learn how to actually create templates, when you are actually dealing with a template, the templates create such a complicated type that recreating it takes a long time. A function returns something that you don't even know what the type is. You have to go through logic and walk through it with difficulty to find out how it works. Let's put it this way. Say I have a template of a class that can print itself. And this template can be created in 20 different ways. And these are all children of a printable object. And my function returns one of these, and I have no idea which one it is. I have to walk through it and find out. But I'm 100% sure whatever it does, it can print itself. That's when I simply say auto A is equal to whatever. It means whatever the function is returning, it will set it to that. Now I can simply say a.print, so not to use it. Auto is going to be used a lot in future. CFGH. Type alignment, we already talked about it. Size of an alignment, we talked about it, right? I think we did. Anyways, it actually tells you what is the alignment of what the type that you want to deal with. So if you write something like this, it tells you 4, which means this integer is aligned by 4. And if I have something like this, struct nums or coordinate, and I'm going to have over here int x, int y, int z, although this structure size is 12 or 24 depending on what is the size of an integer, but the alignment for it will essentially be 4, because at any place it sits, all the integers can sit in an address that is multiplications of 4. Essentially, a line of returns what the address should be divisible by to be able to put this structure in it, or this value or variable, whatever we have. This was a quick review of what we've done before. We good? Okay. Now, I was talking about floating points, and I told you when you're dealing with floating points, it's you have 2 things over here that you need to be careful about. It's how many meaningful digits you can have in a floating point number, and this is how it works. So essentially, for floating points, careful, 7 is the one, which means line number 6 is iffy. Okay, you may lose values. You may lose precision. Same thing for number 7 and number 8. That's 7 digits back to back. You see that? The zeros don't count, because the floating point moving around here is essentially what is it going to be multiplied for. So that doesn't count. In here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It means this is essentially 1.2 multiplied to 10 to to the power of minus 10. Okay? So when it actually gets multiplied to that one, it moves it to left. So where the floating point stands is the number that is being multiplied to. And that's what you need to worry about. So this one will lose value. It's not going to be precise, but this one is. For double, it's 15 digits. Okay? That's standard down to this point. Now we have a long double. They say long double. Actually, let me just over here add something. They say long double is more precise than double. It is not really. Include. It is not really. So how many digits a long double can hold? This is what it is. Again, I don't know if these are in the notes or not. So depending on platform and depending on how many bits they are using to hold the significant part of your double number, the number of digits differs with that. If I run this, you will see that the very first thing that is printed over there is that, in this case, it's 17. So in this platform with Visual Studio, it's 17 digits that it can go up to, my long double. So float was 7, double precision became 15, and then I go to long double, and it only adds 2. So 2 to the power of 2. So be aware of that. So you only can have 2 more digits added. You have to check that and see what the platform that you have actually supports. Depends on platform. So yeah. Again, I'm going to put emphasis on it. The number of digits back to back, removing leading and trailing spaces, is the precision of the floating point numbers. Removing leading and trailing zeros. So if I have something like this, I only have 5. You remove all these. Remember that. Okay, that's floating point precision. So built-in types are types that we have that they extend the fundamental types. These are like pointers, references, and array, okay? So when we say fundamental types, those mean the types that come with the compiler. When we talked about built-in types, these are types that are built up of fundamental types. So built-in types are pointers, references, and arrays. Pointers, we know that. I'm not going to go through it. You know exactly what it is. We can use typedef to shorten the pointers that we want to create. So it makes our life a bit easier, okay? So we can have a typedef like that. So typedef unsigned long integer pointer, okay? And that makes it short. But the equivalent for it, and a better way of doing this, is actually using. So it's better to say using equals to this. So this is the C++ way, and a better way of doing it. Always use using and not typedef. It works everywhere. What happened? Sorry. Okay. So instead of writing typedef, it is much easier to do it like this, and using works with templates and everywhere. But typedef sometimes it doesn't, so be careful. Use using, that's much better. So very useful. Now, we said we don't have a void type, but we do have a void pointer type. What is a void pointer? A void pointer essentially means it can carry any type of address in it without casting. A void pointer is a pure address. It does not know what is the target. So when you have integer pointer, you know your integer pointer is pointing to an integer. But when you have a void pointer, you know it is just an address. It does not know what is sitting at the target. So void pointers cannot be used until they are casted. Remember that. Extremely important. Yes. You have a very soft voice, my friend.
Can I use auto as well?
For what? For void? If you have this, yeah. If I have void pointer p, I can say auto a is equal to p. That you can. A is a void pointer. But it must be, again, auto only works for initialization only. And that's it. Okay? Now, an example for a for usage of a void pointer is getting hexadecimal dumps out of memory locations. So take a look at here. Take a look. I have void hex dump that is receiving a void pointer. I could have received a character pointer and then write it as is. But the difference is that if I write it with a character pointer, people who want to use hex dump, they must cast their memories to be dumped on a screen. The only way not to require casting is to make that void pointer, a void pointer. Then afterwards, obviously, I can actually do create my own character pointer, whatever I wanted, and do a static cast and get whatever value I have. And then I can simply print the hexadecimal dump out of it. So it's as easy as that. So I'm saying I want cout to be done with hex and set fill with 0. Then I'm going to set the width to 2, and one by one start printing all the characters, and that's going to give me a hexadecimal dump of whatever value I had. Simple and straightforward. Okay? And I don't know why I'm returning 0 here. It's void. Sorry, bad habit. Okay? We good? Want me to run it? Yes.
Does the void pointer just point to a defined amount of memory?
It just points to a certain location in memory. That's it.
That's like not applicable to any of the types here.
Okay, let's put it this way. Any pointer is an address, but any address is not a pointer. See, if I say address 46, you don't know what's in there. That's a void pointer. But if I told you integer address 46, then that becomes a pointer that you can actually point to. That's what void pointers are. The reason that hex dump is receiving a void pointer, because it wants to dump any type of memory. Any address you put, it accepts, but not the other way. That's why at line 5, I have to cast the void pointer to a constant character to be able to print it. Otherwise, the compiler wouldn't be able to print it. You good? So that's hex dump. Okay, this is the last thing that I'm going to talk about that is boring. The next thing I'm going to talk about is pure 345, and we need to pay attention for it. So probably I'm going to give you a break before that, okay? So we know references. References are new names for already existing things. We're all good with that? And that's what we learned in C language. So essentially, I create a reference to an already existing variable, and I can refer to that variable using the reference. That gave us lots of comfort, not passing pointers in functions. When I want to change things, I can pass a reference, and my life is much easier. So that's reference. But we need to understand one thing. What is an L value and what is an R value? We need to understand, actually, break. Go for a break and come back. Because we had rule of 3, I'm going to talk about rule of 5 now. Okay? So we need to know that. I'm pausing recording. Please remind me to start again. All right. We need to understand what L value and R values are before we continue. L value and R values are. So if I write over here, integer a is equal to 10, and I'm going to say a is equal to 20, 30, whatever, 20, 30, okay? An L value is something that you can put it at left side of an assignment. Okay? An R value is something that you cannot put at the left side of an assignment. It must be at right side, most of the time. So can I say 30 is equal to A? I can't. Okay? You can extract the reference of A and take it out, right? But you can extract the reference of something that is an R value too. Now, an R value has two ways. I can say over here, integer I set to 10. I can do that, right? And I can say I is set to integer 52. Correct? Now, the thing that you have at right side, you can actually write in left. I can say integer 100 is equal to I. There's no problem with it. First of all, what is line 15, integer 50 do? What does it do? It looks like I'm calling a constructor, but you know religiously that we cannot call a constructor. So what is it doing? It is creating a temporary nameless class of type int, the big one that I've written over there, and sets it to 50. Then it copies that on I, right? At left side, what's happening? It is creating a temporary nameless int out of 100, then sets it to whatever I is, and then at line 17, it dies and goes away. So absolutely I did something stupid. Okay? So this is an object that is about to die. Something that is at the edge of its lifetime. That is considered an R value too. We call that an R value. So when I said R values mostly are at right side of an assignment, and you cannot put it at left, I was telling you the truth. You cannot put 10 at left side of an assignment, say 10 is equal to X, or 10 is equal to 20. You can't do that. But an R value as a dying object can be put at left side of an assignment for some unknown reason. I don't know why you want to do that, but you can. Okay? You understand? So L values are things that are living and they're there. There's nothing wrong with them. You can use them, whatever. You can put it at right side or left side of an assignment. Everything's good. R values mostly can only be at right side, or if it's at left side, there is an iffy situation happening. We okay with this? You okay? Now that we know what R values and L values are, the good news is that we can actually detect them. We can detect if something is being passed as an R value or as an L value. Take a look at this. I'm saying void print, okay? And in here I'm going to say const integer reference n, okay? And in here I'm going to say cout, what am I going to write over here? L value, and I'm going to do an end out. You okay with this? Now take a look. I'm going to write another print, and please pay attention to this. Void print. In here I'm going to say int. I'm going to put 2 ampersands. That means R value reference. And I'm going to put n. And I'm going to do the exact same thing for int. Oh, come on. M value. Oh. Now take a look at this. I'm going to say print A. Then I'm going to say print 100. Then I'm going to say print I. Then I'm going to say print integer 2000, whatever. Okay? Now let's walk through. Holy moly, how many different selections I have over there. All right, so when it runs, as you see, I have the two values here. When I say print A, it goes to the one that receives a reference, an L value reference, and it prints L value 10. But when it comes to the one that is either an R value or a Dines object, automatically it goes to the one with an R value reference. You see that? You good? And in this one, when I say print I, it goes to the one that is actually receiving a reference to the object. But when I come over here, it goes to the Dines object, which is an R value. So R values can be detected. You good? Also, you can do something else. You can say print move A. When you say print move A, you're saying, I know that thing is an R value, L value. I want you to pass its R value reference. So you can always invoke the one that you want to select manually yourself. You okay? So now, on the last one, if I run it one more time, you will see, although this is an L value, but it goes to the R value. Are we okay with this? Are we okay? And also, there is another one that I cannot give you the example for, okay? You'll find out later on what it is. It's called ref. So move gives you an R value reference. If you have something and you want to explicitly extract its L value reference, you can go REF, ref. So you have ref and you have move. We're going to use the ref later on. Okay? Be aware of it. So ref does that. Ref extracts the L value of it. I don't know if, just going to try it. I don't think, it might not work, but I'm just going to try it. Nah, see, it won't work. Oh, wait. Nah, it won't work. Yeah, because you can always put an R value, an L value instead of an R value, right? You can always put it at right side. But the other way is not always possible. That's why you cannot ref it. Ref later on comes, you will see in future. So remember that if you have an object and you know that object is an R value, you can always enforce at all times. And sorry, if you have an L value, left value, and you want to enforce that always the L value function is called for it, you can put a ref beside it. It doesn't make sense now. When we come to reference wrappers and things like that in the future, you will see that it makes a whole lot of sense. Over here, I cannot introduce it because I cannot give you an example for it. But remember, the opposite of move is ref, okay? If you want to extract a reference, that's what you do, an L value reference. We okay with this? Are we okay? So remember ref in future when the time comes. to my close. Oh, it's here. A quick, before we continue with the next topic, let me do a quick covering of arrays and kind of go through it. We know about aggregate initialization and all the good stuff, right? So you can use the aggregate initialization, which is essentially a universal way of initialization that we talk about to initialize any array. You don't need the assignment, you know that, right? And it initializes everything. It initializes everything, and whatever is left over there will be 0. So essentially I'm saying remove this assignment. It's exactly like C, but you remove the assignment and you can set it up. There is no problem with this, hopefully, right? So aggregate initialization, we know it. And the next thing I wanted to tell you before we move to the one that is relative to the move thingy is range-based loops. So we have something in C++ called range-based loops. Now, range-based loops, I actually gave you the example over there. I'm going to put it over here again. Or like this. So take a look at these arrays that we have. I'm saying for int e, and I put the array. You see that? So there's no counter here anymore. Essentially, you are saying, I'm creating an integer called e for element, okay? Go through the array that I'm giving you, set e to every single element in every single loop. So in a first iteration, e will be, let me write it in a better way. In every iteration, e will hold the value of the elements of the array. So e will be A0, and then A1, and then A2, and it comes out and it prints 3. Over here it's going to be 1, 2, and then 2 zeros because it's 5, and over here it's going to print 5 zeros. So range-based loops happen for all collections. The built-in type array works with it too, but later on we'll find out that the exact same thing works for all collections. We're going to learn templated collections, things that we're going to use instead of arrays. We're not going to use arrays anymore. They're more efficient than arrays. And this range-based loop works for those two, okay? And it's much more efficient. So if I run this, it works exactly the same way like a loop. Absolutely no difference, just goes through every single one of them, okay? Now the next thing you need to know about range-based loops is that if you want to change the values of the elements you need to create the iterator. We call this an iterator. You have to set the iterator to be a reference. When you set the iterator just to be E, it means it will be copied. Every element will be copied into it. Therefore, if you change it, the array is not changed. But in here, when I say E, now I can actually add values to it. So I can do something like this. So this not only, it prints it first and adds 1 to it. And if I run it one more time, you will see that the second one has the values added to it. And the third one is not. So it's 1, 2, 3, 4, 5, 6. When I run the program, this is what we see. Oh, I executed the wrong program, sorry. My apologies. One more time. When I run this, this is what happens. Take a look. The first one is actually holding a reference. So, of course, it shows 1, 2, 3, 4, 5, 6 because the addition happens after E is being set to A. But for the next loop, as you see, E is now being set and everything is added by 1. In here, still, I'm adding 1 to the E. But because the iterator over here is not a reference, the copy will be added by 1. And for last one, you see it remains the same. Okay? So remember, when you are doing a range-based loop, first of all, it must be to an array that is in a current scope. You cannot pass an array to a function and then try to write a range-based loop over there. Because you know in C language, when arrays are passed to functions, they become pointers. They are not arrays anymore. So you cannot do a range base by an array that is passed to somewhere else. That's number 1. Okay? Number 2, if you want the iterator to actually modify the values of an array, you must make it a reference. Yes?
So say you did get an array that was passed a function, would you have to make a temporary array using the array passed?
Built-in arrays, you can only do a range base in the same scope. No way to pass it.
But that's what I was saying, that you can take the, like if you got a pointer that is an array, it's passed by a function, you can just make a temporary array and then use that array to.
How can you do that? First, you have to write a regular for loop, copy everything. No, you can't. There's no way to do it. There is no way to use a range-based loop when you are passing an array to a function. It must be done in the same scope. Later, we'll learn when we learn about different types of collections we learn, those collections can be passed and everything works with it perfectly. Range-based loop with reference. Okay. So I have a class called Box. Let me bring these up. So this box of mine is holding an integer data. Please go through it and think about it, see how it works. Oh, I need a function to show the values inside, so let's. Also, it's a brilliant idea to do this. See if there is anything wrong with this. I have a class with dynamic memory allocation. I'm instantiating one with that integer thingy, and it sets it to a value. I have a copy constructor that copies the value, right? And let's do an assignment operator for the two. So we are doing rule of 3. So for the assignment operator, I'm gonna go box reference operator const box reference other. Then we have if, what do we have? If this is not equal to other, and I have returned this, right? So what do? I'm going to say data is equal to, operator equal, okay? Now I'm going to say if, so let's first delete data. Data is equal to null. Okay? And I'm going to say if other, yes?
Semicolon.
Oh, sure. Okay? If other data exists, then I'm going to say data is equal to new int, what is the other one? Other. Did I make a mistake? So I am saying the other, then I'm going to say if this is not equal to other, delete my data, set it to null. If the other one exists, copy it, and we're done. Are we good? Anybody have any problem with this? You good? You okay? All right. Please assume that this int pointer that I created for data is a ginormous thing. Imagine that this is 5 million bytes, okay? Think of it that way. Don't look at it as a single integer. So what I did over here was essentially this. Just to remind you of how this thing happened, is that I have a class box, and this class box of mine had a pointer in it, and that pointer pointed to an integer. Okay? Purpose of making it big. Okay? So what did I do? Now I created for a copy constructor or for an assignment operator, what I'm doing when it's being assigned to something else, when another box is being assigned to this one, what I will do is that if there is anything in here, I'll first wipe it out. Then I'm going to measure the other one, have the exact same size. Then I'm going to copy everything from here to here, and at the end I'm going to make this one point to that one, correct? That's assignment. For copying, the only thing that is missing for copying is that I don't delete anything because it's a brand new object. We good? Are we okay? Now to this point? Now I want you to please pay attention. Oh, look at this, the microphone is here. I hope it lifts here, hurt me. Anyways, so Are we good down to this point? In reality, that's not what's happening. This is a water bottle. If you have a water bottle, what do? Do I go create water and give you the exact same amount of water that I have in here in yours? That's not what's happening. I open this up, I pour my water in your cup, and then therefore you have water, correct? I move the data from here to here. That's reality. And that's much less time consuming. For you to actually do whatever we have done in OOP345, if you wanted to copy if you had a cup of coffee and you wanted to give it to someone else, you had to take the person's cup, go to Tim Hortons, fill it to the exact same amount of coffee that you had and give it to him. You copied your own. And then you throw your own away with the coffee and everything. Does it make sense? The proper way of doing it, if you are not to use yours, if the person says, I want a coffee like yours, yeah, in that case you copy. There's no problem with it. You want him to have a coffee, you want you to have a coffee. But if you want to give your coffee to someone else, it's stupid to get the same coffee and throw yours away. It's better to move your information to that person. Does that make sense? So essentially, what I want to do, instead of having this nonsense that I have done over here, when someone else has an empty cup, all I need to do is to wipe that out, make that thing null, and then make mine point to that one. Done. Right? So empty the data from the, so essentially take ownership of the other person's data. I wish only I could detect when do I need to move the data. Oh wait, we just learned that. I can actually do, instead of this copy constructor that I have over here, I can say, hey, wait a minute. I want a box. I'm not going to make it constant because I want to empty the other cup that I'm copying. So this is going to be a box, but I want the one that is movable, 2 ampersands. Then in here I'm going to call it other, right? Now I can say my data is initialized with the other's data. Good? So what did I do here? When I'm copying this, I simply saw where it's copying and I'm going to put it over there. So no dynamic memory allocation happened. I just set my pointer to where the other pointer is pointing, correct? Right? Now I'm going to say, hey, you have no longer access to it. Done. So instead of copying and all the process that I had, I simply took over the ownership of the other one. Same for the assignment. Look at that. I'm going to say, okay, this is box, reference, operator, box, reference, right, other, okay? And for the reason that I cannot explain, you will find out at the end, yes?
But not equal, operator equal.
Oh, yeah, I'll put that one, thank you. I miss your corrections in all the other classes, Harris. Okay, all right, so what I want to say? Yeah, so when you are doing this, it's a good idea to write over here. no except. Why? Because the sky is high. Just put it that way. Okay, just put no exception. Why is it giving me an error here? Expected the declaration. What's going on? Oh, wrong place. That's the one. Yeah, okay. And here the same. So in here, this no exception, you're going to learn what it is when we do exception handling. If you don't put it, it will still work perfectly. So I'll remove it and I'll run it. It will work, but it might give you a warning. Now, again, I want to move something to myself. It's exactly the same thing. I'm going to say if this is not, so I don't want to move anything to myself, not equal to address of other. Okay? No dynamic memory allocation. I'm going to say my data will point where the other data is pointing. I don't care if it's null or not. Okay? Of course, I have to delete mine first. There's no problem with that. But I'm just going to set my data to point the other's data. And as soon as that is done, I'm going to say other data is null PTR. Done. Of course, return this. This is called move constructor and move assignment. Essentially, it means specially, so you can always move stuff manually. So you can have one class, and then you can move everything to another one, even if they both exist after the operation. So if you have box A, box B, if you say B is equal to move A, instead of assignment operator, it's going to call the move assignment and move it. But if you have a temporary object that is about to die, then it knows that it's supposed to be moved. Because it's dying, why should I keep it? It moves its data and therefore less. Like this, the process of especially returning ginormous objects becomes extremely fast. Imagine that you have social insurance number of all people in Canada, and you want to return subsets out of this one using functions. Okay? So what you do, you go to a function, you receive the array of 35 million social insurance numbers, and then you build a dynamic one based on a criteria, and you have a subset that is only 10 million. And you separate the 10 million and put it in an object. And you want to return that object. You know how long it's going to take if you put this thing in a loop over and over? But if you have moved this thing out, which means if the object you are collecting the samples in has move constructor and move assignment, when you return it, it will automatically be moved because it knows it's about to die. Therefore, it will move the data. No 10 million, nothing will be copied. It will simply point to the data of the other one, and the other one will be set to null. And therefore, it's going to run hundreds of times faster. We had rule of 3 in OOP345, which was, what was rule of 3? Copy constructor, copy assignment, destructor. Now we have rule of 5. Every class you create must have rule of 5 implemented. Copy, assignment, move copy, move assignment, and destructor. Like that, your object not only is memory safe, but also it's quick when it's supposed to be moved. We good? And believe me, all the objects that you have that are created in standard template library and stuff, they all support this. So yeah, so I can write a main over here for this. Did I do, oh, it's a semicolon I think I need in here. So now I have a box that is 42. Now I'll say box B is equal to A. That's going to be copied. So B will be copied. B will be a copy of A. But then I can say box C is equal to STD move. That is going to move A into that one, which means A will have nothing afterwards. So in here, I can do this. Oh. A.show. So you will see that A has something in it, and not only that, not only that, I can even do this afterwards. I can say C will be set to move of B. And now, after this, you will see that the data is moved into C. And also, you can always say A is equal to box and what that does is exactly the same thing, because box is a temporary nameless object. It will get constructed over here with a 2000, but when the assignment is being passed, it's not going to get deallocated. Simply the 2000 that this box is pointing, A will point afterwards. So running this program, this is what we are going to see. Let me just clear all. Okay. So we come through. Box is created. This one is created and it will be copied. So it actually goes to copy constructor and copies the other one. Now we have 2. Now we show A. A has 42. Now I'm going to say CB move A. It goes to the move constructor. It will transfer the ownership of the other one into here. So data is now pointing to that one. And this data that is pointing to 42 will be overwritten with 0 and it comes out. Now B has 42, C has 42, and A's got nothing. Now I'm going to move B to C, therefore it comes to the move constructor, and that's the other. It deletes the data of B, of whatever at left side, and takes the ownership of the other one and sets the other one to null and returns it. Now if we look at it, B is empty, C is 42, and A is that one. Now I'm going to move B 2000, so it actually creates one data dynamically, then passes it to other. So other is that temporary nameless. The temporary nameless, the current data will be deleted. The temporary nameless data will be owned, and the data of the other one will be null. It goes out, and as you see now, empty is 2000. As simple as that. So move construction is extremely important, and we need to understand it perfectly. Okay? So move semantics, rule of 3. Please review it. And a perfect practice, create a class called name. Okay? Have that name have dynamic C string as its data. Then implement the rule of 5, pass it around and see what happens. Okay? Rule of 5. Okay, next. Need to talk about static variables again, but this time, what if they are members of a class? When you create a static variable inside a class, that variable will be a shared property between all instances of the class. So if this is your class, and an object, then when you say static int count, this will be your count. And all these objects will share it. It belongs to all of them, and it belongs to none. They share the value. Got it? Because of this fact, none of these classes can actually instantiate it. You cannot put it in a constructor. The constructor of a class cannot create a shared property. Because of that fact, you have to do it manually yourself at the bottom of the class. So you have to say, hey, that integer counter count, create it and set it to 0. So the creation of static property must be done separately under the class by themselves, because they have nothing to do with an object. They are class variables, not object variables. Got it? Constructors build objects out of classes. Because static variables are shared and they are class variables, constructors can set them, but they cannot build them. They cannot create them. Now, if you create a static method inside a class, the static method can access the count with absolutely no problem. But you cannot access non-static values in there. Why? It's very simple. When you create objects out of the class, the method that you see over here that is called getCount, that will be a separate, that will be a separate function of its own. So this is your getCount. Like a static property is not a member of any of the objects but the member of the class. Therefore, it will be created separately on its own. And because of that, if you try to access any of the properties inside the class, so this is the data, and data. If in getCount you are saying data, getCount's going to say, which one? There is no access to it. You cannot. Therefore, you cannot. Only static variables are accessible by all methods, but regular variables can only be accessed by regular methods, not by static ones. So this essentially will be an error. So in here, what I have done, I actually created a counter of objects. So what happens in here is this. Because the counter is set to 0, the class, when there is nothing in it, if I say, hey, how many getCounts I have, and please pay attention, I am calling the static method using the class name, not the object name. I'm saying counter scope resolution getCount. You could use a an object name, like a regular method, but it makes no difference. It is the same. A count, counter count are the same. Absolutely no difference. So by doing something like this, I'm actually counting how many objects are created. When I start the program, because the counter is 0, nothing happens over there. When counter A and B created, because the constructor is called twice, then it's going to actually add 2 to the count, and therefore get count's going to say 2. Now I can even do this. I can do this. So that's actually going to be 3 now. I can do this. Now it's going to show 2. So what happens is that 3 times the constructor is called. So let's call it and see how it works. As you see, count is 0. Now these 2 are created, and the dynamic one is created. Therefore, I have 3 objects. I delete the dynamic one. Therefore, the destructor call. Therefore, the counter goes down. Now I have only 2. Okay? So it actually counts how many objects of that type is created. We good? We okay?
So you can only adjust that static variable using the constructor when the other object is made, or can you make a method that can adjust the static? So like if you wanted to change the counter, can you make a static method to change it?
Yeah, of course you can. Statics can access statics and change them if you want to. But if you want, you can do. So it's one-to-many relationship. Remember that. Many can access 1, but 1 cannot choose which one. Therefore, it cannot go back. One-to-many relationship is always a one-way thing. Now, when you create a static method, then it becomes one-to-one. As easy as that. Oh. Static methods and attributes. That's that. Say I want to write a program, and in my program, I want to refer to days of the week. So what do? I can go C style and write define statements, say Monday is equal to 1, Sunday is 1, Monday is 2, and keep going like that. Or I can use a construct called enumeration. By doing something like this, by writing something called enum, what you can do is actually this. You can set, you are essentially saying color is an enumeration of white, red, green, and blue. And it automatically starts the first one with 0, sets the next one to 1, 2, and it keeps going like that. Now, white becomes literally a constant integer. You cannot use it anywhere anymore. It becomes part of the language as a constant integer. So that white thingy cannot be changed anymore. You can have, you can create over here color, C, and you can say C is equal to red. Okay, but that doesn't mean that you cannot say C is equal to 3. You can do that. Remember, white is 0, red is 1, 2, and 3. Now in new C++, when you are doing, because of new type safety, this will not be allowed. If you go back to C language, by the way, this has nothing to do with C++, this is C language. If you go to C language, line number 11 is allowed. In C++, because of type safety, it is not. But it is, nonetheless, it is the same. Okay? So, allowed in C, but not C++. If you go C++ 99, before C++ 11, it is allowed. But as the language became more type safe, they removed that. So essentially, I can actually write a program like this. Overload OStream and color, and pass a color, and actually make my main show different colors as we go like this. So wall is red, ceiling is white, door is green, and I can go like that. And one by one, it's going to show, of course, it's going to show wall. It just shows the numbers. Okay? All right? So based on those values, it's going to show it, and it's going to show the colors and so on and so forth. So that's how enumeration works to give meaning to things that you have. In C language, we used to use the same thing for Boolean. We used to write enum, so we did this in C. We wrote enum, Boolean, and they would put false and true. So essentially, now you have a type Boolean, and false is 1, and true is false is 0, and true is 1. As simple as that. Okay? Now, if you wanted to, you could always reorganize these things. So I could say, I want white to start from 10. You can always do that. There's no problem with that. If you do like that, then white becomes 10, red becomes 11, green becomes 12, and blue becomes 13. Yes?
How about only red change to 10 and white is 0 to 0?
So if that's the case, then you can leave the white as is and make the red 10. Now, white is 0, red is 10, green is 11, blue is 12. Got it? So whichever you initialize, it starts from there and sets the rest one more as it goes through. Are we okay? This is called enumeration. But this is C. RSTU, I think we are running out of alphabet. V, so C enum dot CPP. In C++, because that white thingy becomes available everywhere, they say that sucks, we don't want it. When you create something like this, I do not that white to be initialized to a value and not usable anymore. Nobody can create a variable called white anymore because white becomes a number, a constant number everywhere in the language. So what they did, they said, we can do this instead. In C++, instead of just enum color, you say enum class color. And after you do that, now your white, red, green, and blue become part of the scope color. So you have to say color scope resolution white, color scope resolution red, and white is not accessible as you see everywhere. Again, makes it type safe. And that's all that is. Are we okay? C++, enum. We're done. So week 2 is finished. Please go through the notes of week 2, those 3 things. See if there's anything missing. Let me know, and I'll cover it the next day. Have yourself a beautiful day. And let me stop the recording.